So, in today's lecture, we continue our discussion on vapor liquid equilibrium. So, if you recall, we talked about degree of freedom. Okay, so if you have binary components, and then if you fix pressure and temperature, then the mole fraction of two components in liquid and vapor phase will be fixed. Okay, so we apply this rule, degree of freedom F equal to C minus P plus 2. So, which means if T and pressure are known, mole fraction of A and B in V and L two phases will be fixed. Of course, we can apply Rawls law and equate with the total pressure or the partial pressure to calculate X and Y. In today's lecture, we do this, we prepare TXY diagram. So, if you recall, in absorption also, we started with the thermodynamics. So, first thing is that we must establish the equilibrium conditions between the two phases. So, in other words, given mole fractions of Y, given mole fraction of A in vapor phase, what is the mole fraction in the liquid phase for one component or for both components. So, the first thing we have to do in this distillation, the second unit operation, is to establish this TXY diagram. Okay. So, for this one has to do the experiment. So, in a batch experiment, you start with a system of liquid A plus B, heat the liquid and monitor its composition and monitor the amounts of liquid and vapor formed in that closed system, and then plot this TXY diagram. Okay. So, one has to do this experiment, and one can also apply this Rawls law to corroborate his finding or observation. So, we will do this exercise here in plotting this TXY diagram, which is the first thing one has to do before we get into this distillation column. Okay. So, let us start with this TXY diagram, which will look like this. So, essentially this is what we want to plot here, or we want to establish here. We have temperature here and we have mole fraction of A in liquid and vapor phase. All right. So, what we are looking here at a batch system. Suppose we take a batch system here of liquid, say L A plus B. There will be some amount of vapor in contact with liquid here, also containing A plus B, and if we heat this liquid slowly. All right. So, if you have, say, pure component of A or B, say Xa is 0 here, and if it's 1 at this end. So, if you take pure component of B and heat it, you will expect that at boiling temperature Tb, corresponding to the total pressure Pt, the system will boil, or this component B will boil. Similarly, if we have A, pure component A, mole fraction 1, and you heat this liquid, then at a certain temperature corresponding to the boiling temperature of A, right, the component A will boil here and will vaporize, an entire liquid will convert it into vapor. So, when we have the component, binary component of A plus B, then start with certain mole fractions and heat this system here. One can do this experiment, one can monitor the amounts of L and vapor and mole fractions and or compositions, mole fractions of A or B in two phases. Essentially, one can monitor Xa and Ya. So, 1 minus Xa will be the mole fraction of B, and 1 minus Ya will be mole fraction of B in vapor and the liquid phase. Okay. So, if you do this experiment, what we observe here, that as we increase the temperature, okay, a certain temperature is reached at which the first bubble is formed. Okay. So, this is very important that we understand the difference between the boiling of a binary components and the boiling of a pure components A and B here. Okay. So, when we take this cold fluid liquid and we increase the temperature is reached here at which the first bubble is formed. If we choose another mole fractions here, so let us say some mole fraction is smaller than this, and heat this liquid, we will get another boiling temperature here at which the first bubble will be formed. Essentially, we will have a locus of all boiling temperature like this. If we take another mole fraction here and heat it, we have another boiling temperature. So essentially, we have a locus of bubble points curve. Okay, so we call it bubble points curve. Okay, so what is a bubble points curve? It's a locus of the temperatures depending upon the mole fractions of A in the liquid phase at which the first bubble is formed. First bubble is formed. All right. So this is the temperature at which the boiling just starts taking place. If we further heat it, okay, then we will see this very significant amount of vapor is formed. In other words, now we will have two phases, one vapor containing A plus B, and another phase we have the liquid containing A plus B also. In this case, the amount of liquid and vapor will be different. One can measure this amount of liquid and vapor. One can also measure the composition of A in vapor phase and the liquid phase. Now we have now two phases here. All right. So this is a liquid. Now we have L plus V, the liquid phase and the vapor phase. If we take another mixture here, let's say we have heated here, we reach this bubble point, we further heat, then again there is just separations. Observe, we have some amount of liquid form, some amount of vapor form. We will talk about this later. What is the total amount? Essentially, we have now another locus. All right, curve like this, in which for a different compositions there will be a separation of two phases in vapor phase and the liquid phase, in which the amount of liquid and vapor is different, and amount of vapor compositions and amount of liquid compositions are different here. Now if we further heat it, continue with this heating, then temperature is reached at which the entire liquid is now converted into vapor. So similar to all this bubble point curves, we have a locus of what we call dew points curve. Dew points curve. Okay, so this is dew points curve. Now what we have here is when we reach this temperature for this binary components of A plus B, depending upon what mole fraction we are starting here, is the temperature at which the entire liquid is now converted into vapor phase. So essentially for this binary phase there is a temperature range, right? One is TB for a pure component B, and we have this boiling temperature for a pure component A, and if we choose any binary components of A plus B, a mixture of A plus B, then there is a temperature range between here and here. All right, so there is a temperature range at which the boiling takes place. First boiling or first bubble is observed at certain temperature, we call it bubble point. We further heat it, there is separations, liquid plus vapor. The vapor phase contains so much mole fraction of Ya given by this curve here, and the liquid phase will contain so much mole fraction of Xa given by this curve here. If we further heat it, boiling continues till we reach this point, and entire liquid is now converted into vapor phase. This temperature we call it dew point curve. So we make three very important points here. One, there is a bubble point. This corresponds to Xa in liquid phase. So this is the temperature at which the first bubble is formed, or the liquid just starts boiling. After that there is just phase separations. There is a phase separation, or we have liquid plus vapor mixture, in which you can see the vapor phase composition is greater than feed compositions, if you call it ZF, which is in turn is greater than Xa. So let's see what we're trying to say. Suppose we start with certain mole fraction here. Okay, so this is, we call it ZF. We start with the composition of feed with ZF mole fractions, say 60% of A, and we start hitting it. First we will reach a bubble point. So this is a temperature at which the first bubble will be formed. We further heat it. Now there is a separation, L plus V here. We call this as a tie line. Okay. Now there is liquid and vapor form. Vapor phase composition is given by this Ya, and the liquid phase composition will be given by Xa. You can see Ya is greater than Zf and Zf is greater than Xa, which means there is a enrichment. We are starting with 60% mole fraction of A. Now we have been able to achieve 80% of A in the vapor phase and 40%, for example, lesser than the feed composition in this liquid phase. So this is essentially we have Ya greater than Zf greater than Xa. And here also one should note that with the boiling temperature of B is higher than the boiling temperature of A, because vapor pressure of A is greater than the vapor pressure of B at any temperature. Okay, so we have the boiling temperature of A smaller than the boiling temperature of B. That means there is a temperature range. There is a del T which is in between the boiling temperature of a pure component B and the boiling temperature of A, over which the boiling takes place. Boiling takes place, and as a consequence, similar to this bubble point, there is a dew point. So dew point is a temperature or is the locus of different temperatures at which entire liquid is now converted into vapor phase. So starting with liquid, we have now liquid plus vapor, and then we have this vapor phase. We start with certain composition ZF. At any instance, liquid has Xa, vapor has Ya mole fractions, and now entire liquid has been converted into vapor, which means the final composition will be same as the starting composition which we have ZF. Okay, the same experiment one can also do starting with a vapor, which means here we start with a liquid in a closed container, fix the pressure, composition is 40% A, 60% B, heated. So the temperature is raised from room temperature, for example 30 degrees centigrade to 80 degrees centigrade. When the temperature reaches 80 degrees centigrade, one can physically observe that now the liquid has started boiling or just about to boil. That point is your dew point, and this dew point will depend upon what is your mixture composition. If we start with some other composition, higher compositions, then if we increase the temperature, now the dew point will be formed, or dew will be formed at a temperature lower than the previous temperature. So just follow this curve qualitatively to understand this physical meaning of this. Now we have in case of binary mixtures, there is a temperature range at which over which the liquid boils before it converted into vapor phase. So we start with A plus B pure liquid, first bubble point, further heated. Now there is a vapor phase and the liquid phase. One can calculate the amount, one can also measure the amount to make it, to ensure that it's consistent with our material balance. So we have certain amount of vapor form, certain amount of liquid form. Vapor is now enriched in A. That means the vapor composition given by Ya is now greater than the Zf initial mixer concentrations, which in turn is greater than your mole fraction. You further heat it, liquid is still, the mixer is still boiling, more amount of vapor is formed, less amount of liquid is now left in the container, till you reach a temperature which we call it dew point, at which the entire liquid is now converted into vapor phase. Now the vapor phase composition will be, it's natural that it will be same as what we have started. So you just follow this vertical line here, and every point in between del T, dew point, and the bubble point, there is a tie line. The tie line decides how much is your mole fractions of A in the vapor phase, how much is the mole fraction of A in the liquid phase, and also decides how much is the amount of liquid and vapor form. We'll talk about this later. Why it's called dew point? Because I was talking about this earlier, that instead of doing this experiment from liquid to vapor, one can start with the vapor phase. So superheated vapor. A vapor temperature is greater than the boiling temperature of less volatile component, which is B here. That's why it has a higher temperature. So we have TB and we have TA here. Okay, and you take a temperature higher than this TB and start now cooling it. just do it reversibly. If you cool it, then you reach a temperature which we call it dew point curve, at which the first dew is formed. That means the first drop of the liquid is formed. Okay. Further cool it, there is a separation, vapor, liquid, it follows the same exactly fast until you reach a further cool it till you reach a bubble point curve, at which the entire now this liquid and entire vapor has been converted into liquid. So now I start with the vapor, L plus V, and you have Le. Okay. So this is what we have, this TXY diagram one can observe experimentally. If you can measure the amount of liquid vapor form, we can do some chemical analysis to find the composition of vapor and liquid to obtain this. But you must not forget that this curve can also be obtained analytically by applying this Raoult's law. So let's redraw this curve and make similar observations what we had in case of heating the vapor. So heating the liquid. Now let's start with the vapor and let's follow the locus of this line. Okay. So now we have TXY diagram. So here we are trying to understand the change in the compositions if we have condensation. In other words, we are starting with the pure vapor. So let's say we have this general TXY diagram like this. We have fixed total pressure. If we write TB and TA like this, that means we are saying that vapor pressure of A is greater than vapor pressure of B. It's more volatile compounds, and as a consequence, boiling temperature of A is smaller than the boiling temperature of B here. All right. So now let's see if we start with a pure vapor. Say the compositions of this pure vapor is ZF, and start cooling it. All right. So when you start cooling it, what will happen? The first bubble, first dew will occur right here. Okay. And if so, we call it dew point curve, which is nothing but the locus of all such dews here. If we start with different compositions, the first dew will appear here. If we start with different compositions, the first dew will appear right here. So we have this locus which we call it dew point curve. All right. So now if we further cool from here, then we will get a liquid and vapor mixtures here. All right. So we can call this as XA. We can denote this as YA. The idea here is that the amount of liquid form will be in the ratios of this by this. So it's all tie line. And we can apply the lever rule which we discussed in the previous slide here. If we further cool it here, the amount of liquid will be more, and all the time the ratios of the liquid amount and the vapor amount will be given by this ratio, If we keep on further cooling it till we hit this point, we can say that we have hit what do we call bubble point curve. And we further cool it, we have now this pure liquid. So starting with pure vapor, we have L plus V, then we have this liquid. The idea is that either we start from the pure vapor to reach the zone of pure liquid through this L plus V by condensations, or we start like in the previous class with the pure liquid and heat it till we reach L plus V, and then we have this pure vaporism. Both of them will trace the same TXY diagram in a general curve like this. So either you go from here or you start from here, it will give the same results. Okay, we can make a note that all the time vapor is rich in A. It's a more volatile compound. We said the vapor pressure of A is greater than vapor pressure of B, or the boiling temperature of A is smaller than boiling temperature of B. And all the time liquid fraction is rich in B. So we have this TXY diagram, either way starting from the pure vapor or heating of this pure liquid. Okay. So we will like to redraw this again. So let us redraw this TXY diagram. So we are plotting XA and YA, 0 to 1. We have TB, we have TA. This is the bubble point curve, and this is dew point curve. If we take any compositions of ZF and we reach this zone of liquid plus vapor, we have compositions given by this bubble point curve, bubble points curve given as x, and we have this composition y given by dew points curve. Okay, so this is, we are calling it tie line, because we are going to apply what do we call tie rule here. And of course we know that if we further heat it, then we will reach this dew point curve, then the entire liquid will be converted into this vapor phase. So there is a boiling temperature range for a binary component. For a pure component, entire liquid gets converted into vapor at one temperature. For pure A, entire liquid gets converted into vapor at one temperature. However, for a binary mixture, there is a temperature range between TB and TA at which the entire liquid boils. So this composition for ZF, this composition, can say that this is del T range of temperature at which the boiling takes place. First boiling starts from here and ends here. Similarly, if we condense, first condensation takes place at this temperature, then entire liquid is converted, the entire vapor is converted into liquid at this temperature. So this is a temperature range for this binary component mixtures. Okay, so if you are doing this batch experiments and start with some feed of A plus B, at any time we can write that F equals L plus V. All right. So at any instance between here and here, feed is now converted, or feed has two components. So initially we had 100 moles. Now we are saying that part of this 100 moles has liquid phase, and part of this has a vapor phase, and part of this has a liquid phase. So we can make a material balance to say that F equal to L plus V. All right. So we are looking at starting with, now we have vapor phase and we have liquid phase. We started with a pure, say, one liquid phase F, which consisted of A plus B, and we heated it. We have heated it to bring it two phases L and V here. Each phase A, L and vapor will contain A plus B. So now we have made this, we have written this total material balance. We can now make a balance for A alone. So if we have F and starting composition was ZF, so F dot ZF. This would be the moles in this, moles of A in this feed phase. And now this is distributed in liquid and vapor phase. So this is Y, this is X, this is Z. So now you should be able to understand the meaning of this tie line, that this tie line, horizontal tie line which you have drawn here, corresponding to the ZF anywhere in between. All right. This gives you Y1, X1, Y2, X2, Y3, X3 over this temperature. So essentially this A is distributed now between the liquid phase and the vapor phase. With these two equations, one can write L over V as Y minus ZF over ZF minus X. Okay. If we choose, say, this O in between, and we call this as a V, vapor, which is a point, which is the coordinate on this dew point, and we call this, for corresponding to this O or V, if we have L on this bubble points, it's nothing but Y minus ZF is nothing but OV, and ZF minus L is nothing but OL. All right. So this is what we have. So we have this Txy diagram. At a given pressure, we have fixed the pressure. We have this Txy diagram, Tb, Ta, and let's do this calculation for ZF. So this mixture has been brought to this temperature. Now we have O, this point here, this is V, this is L, this is Y, this is X. So Y minus ZF is nothing but OV, and ZF minus X is nothing but OL. So L by V, amount of liquid form, ratios of amount of liquid form to that of vapor is given by this tie line, OV by OL. This is what it says. If we know the compositions of Y and X, the vapor phase, we know the feed composition ZF and ZF, one can obtain the ratios of L and V form. Since we know the amount of F, one can calculate out of 100 moles, maybe 40 moles are liquid, 60 moles are vapor, depending upon what temperature the feed mixture is. And follow this locus, the way it moves. If we further heat it, now we are here. ZF is fixed, all right, but now we reach V here and reach L here. Now look at this ratios now. O has reached here. Now we have new Y, Y minus ZF, and we have new X, ZF minus X. So every time amount of liquid and vapor, they change as you increase the temperature between the first bubble point and the dew point. And how does the liquid or vapor amount change? It is quite expected that in the beginning you have pure liquid, L is almost equal to F when the temperature reaches bubble points, and as you further heat, more and more amount of vapor is formed. So the tie lines you can look at this L by V, right? Now you have this small segments becoming larger here, all right. So let's redraw this and follow how does the segments of tie lines they change. So you have tie line here. Suppose you are starting with the ZF. You have just a very small amount, very small increment in temperature. So now we have this so this is a tie line. ZF is fixed here. This is V. This is L. Further increase. Now we have another V, another L. Further increase. Now we have this. So follow the segments. This segment, this segment, this segment. It decreases. This segment, this segment, this segment increases. All right. So this is what we wrote here. L by V equals OV over OL. Or we can write L into OL equals V into OV. Or L into ZF minus X equals V into Y minus ZF. So what we have here, L, this is L and this is V. L into this. So we are applying essentially a lever rule, or this is also known as tie rule. The amount of liquid and vapor form, it varies along this. Initially we have very small amount of vapor form, then the vapor amount increases till it reaches here and everything is now the vapor form. Okay, so starting with pure liquid, we have reached now the vapor. The amount will be just inverse of the segment. L by V is now OV. If all this locus is for ZF is O, then L by V is OV over OL. So you should monitor this. One can do this experiment. One can also apply this material balance, and to determine how much is the amount of liquid and how much amount of vapor is formed, what is the mole fraction of X and what is the mole fraction of Y. We should also note that this is consistent with our we talked about this degree of freedom. We fix the pressure, say 1 atmosphere, and any temperature between the boiling temperature of A and the boiling temperature of B. If you assume that A is more volatile than B, that means the vapor pressure of A is larger than B and the boiling temperature of A will be smaller than B. So if you choose any temperature in between, right, for a given pressure, then Y and X is fixed, given by the tie line. And once Y and X are fixed, we know the initial amount of mixture, the compositions, amounts of liquid and vapor, they are also fixed. So it's all consistent with your degree of freedom. Fixed P and T, X and Y are fixed. Okay, degree of freedom is 2 here. So the idea of this small exercise is to generate this TXY diagram. Say we want to distill acetone from methanol, water from benzoic acid, acetic acid from formic acid. So there are 2 binary components. One can create this TXY diagram by a batch experiment. If you know some chemical analytical tools to measure the composition of vapor and liquid, for example gas chromatography, liquid chromatography, one can also find the amount of liquid and vapor, one can generate this TXY. But TXY diagram can also be generated by Raoult's law, which we will do in a minute here. All right. And this is also very important to note that instead of this batch experiment which you are doing in a closed system, suppose you do this experiment in open vessel. That means as soon as you start with a liquid and you heat it, once the vapor is formed, you remove the vapor. Again heat it, again you remove the vapor. Or alternatively, you start with a vapor phase of A plus B and lower the temperature till it reaches this dew point. Okay, that time as soon as the liquid amount is formed, you remove it. So essentially, one can do this experiment in open vessel. If you do this experiment in open vessel, what Txy will obtain, that's very interesting, and you should must understand that this is consistent with your experiment. So if you do this experiment in an open vessel where you remove liquid or vapor, remove liquid or vapor as soon as it is formed. Okay, so if you do this, it's not difficult to understand that now we have this T x y diagram. If we start with a vapor, suppose it condenses here, that's your first dew point, and remove the liquid. Now further cool it. Now we have the locus which will go like this, because you are removing the liquid as soon as it is formed. So there is no liquid here. Of course, there is a phase separation. There will be vapor and the liquid like in the previous case, but you are just removing all the liquid. Similarly, if you start with a vapor with a liquid phase, say same compositions, and as soon as the vapor is formed, you remove it, you will follow this path like this, which is same as Tb and same as T. All right. So this is very similar to what we have in the previous case, except you are removing the liquid form or the vapor form here as soon as you reach dew point or the bubble point comes. Okay. Now what we will do next is we will show that this Txy diagram one can also calculate from or obtain from Raoult's law. Okay. So experimental observation is one thing. For most of the binary components, you look at the Perry's handbook, or you look at the Treball's or Maccabee-Smith, they have given this Txy diagram. Okay. If you have a new system, say A plus B, new type of liquid mixture, of course one has to do this experiment. Otherwise, one has to rely on this vapor pressure curve and Twine equation, which you must have done in thermodynamics, to calculate this vapor pressure at a given temperature. So, but still one can calculate Txy diagram by calculation. So let's see how we can do it. So these are the governing equations. We are fixing temperature. That means we are fixing vapor pressure and of A and vapor pressure of B. So for example, we have this Twine equations, or you have some handout tables to calculate or estimate the vapor pressure of A and B. Okay. So total pressure is PT is fixed. That means the partial pressure of PT will equal partial pressure of A and partial pressure of B. What is the partial pressure of A? Raoult's law, assuming ideal gas law, ideal systems, we have XA, PA0T. And similarly for PV, we can write XB as vapor into vapor pressure of P. So we are assuming the ideal components, they behave as ideal solutions. And XA PA0T is the partial pressure, which can also be equated as YA into P. So essentially partial pressure in the liquid phase we have equated with the partial pressure in the vapor phase. This will also equal to YB into P. So T is fixed and PT is fixed too. And what are the unknowns here? Unknowns are XA and YA, because XB is nothing but 1 minus XA and YB is nothing but 1 minus YA. So we have two equations. So these are the two equations we have. And we have two unknowns to solve for XA and YA. So one can solve for XA and YA for different temperature to obtain this Txy diagram. So essentially we have this Txy diagram generated for a binary component of A and B at a given pressure Pt. I choose basically 1 atmosphere, 2 atmosphere, and choose a temperature. I have y and x, y and x given from dew point and the bubble point. Okay. So this is a small exercise we have done, a small calculation we have done to calculate x and y for a given pressure and temperature. Of course, we need to know the vapor pressure of A and B given by some correlations or Einstein's equations or from some handout. Now, in principle, it's also possible that we plot Pxy. In other words, we say that temperature is fixed, and if you vary, pressure. There also we have the same degree of freedom too. If you apply, the rule of what degree of freedom, if P equal to C minus P plus 2. So if you fix temperature and vary P, one can also obtain Pxy. But generally Pxy is not very popular or not very convenient to calculate calculation in distillations. One extensively relies on Pa and Xy. But theoretically one can also plot Pxy. And if you plot Pxy, you will get curve, this equilibrium curve Pxy like this. So now we have same xa, ya, 0, 1. Now if we vary the mole fraction of xa, then it's not difficult to show that the partial pressure of A will vary like this, and the partial pressure of B will vary like this. Okay. So what we have plotted here is partial pressure of A. So Pa one can write as Xa, vapor pressure of A at any temperature. So it's linear. Similarly 0x0, that means the vapor pressure of pure component B, which would be Pab would be 1 minus Xa into vapor pressure of Pt. So with this one can then plot Pt versus x and Pt versus y. I leave this as an exercise to plot this. We have this Pt versus x and we have Pt versus y. Alright. So this is also equilibrium for equilibrium curve for the binary mixture of A and B, Txy instead of Txy. But generally I just said earlier that Txy is more convenient to use and widely used, is more popular. Okay. So in distillation there is one more variable called relative volatility, which is widely used in several calculations. If you recall, we said that if you have a binary components of A and B and we plot Txy diagram, A is more volatile, so it has a larger vapor pressure than B, so it has a smaller boiling point than B. Alright. So larger the volatility, you will see that larger is the separations. So we like to plot this Txy diagram for different volatility as well. So let's define this relative volatility. So relative volatility, which is used, nomenclature is used as alpha, A, B. So relative volatility of A with respect to B is defined as y star over 1 minus y star. So star means it's an equilibrium with x and 1 minus x. In other words, for A and B, this would be ya over yb over xa over xb, or which would be same as pa over pb. So if volatility must be larger than 1, in fact much larger than 1, much larger than 1, if A is more volatile than B. Okay, and one can also show that if alpha equal to 1, that means y star equal to x and there is no separation. No separation is possible. So this alpha relative volatility signifies to what extent A is more volatile than B, or from the practical point of view, to what extent separation is possible, right? So this Txy diagram which we have plotted for temperature in x and y can also be plotted as y versus x, and we will do this by taking the projections of x and y from Txy plot. Okay. So let's again redraw this Txy diagram. So we have Txy diagram like this, which is TB here and we have TA here. Okay. Now just underneath this, let us plot y versus x, right, where y and x they are in equilibrium phase. So we are talking of vapor phase, L phase, liquid, y and x in equilibrium. So liquid and vapor they are in equilibrium phase here. So very often we use y or y star here. Now in Txy diagram, as we said earlier, if you choose any temperature between TA and TB, say this temperature here, then we have vapor phase, this is V, this is L, you have L plus V. Okay. Now all it means that there will be two phases, vapor in the liquid, and the vapor will have this mole fractions, and this liquid will have mole fraction of A in the liquid phase, and here we have this y and this x here. Now if you want to plot y versus x, the best would be first to draw this 45-degree line here. So this is a 45-degree line, and we take this projection here x, and corresponding to this x, this liquid phase, vapor is in equilibrium, so this y we can extend here to 45-degree line and move in this directions to obtain this coordinate here. Suppose I choose this temperature and this tie line, we have x mole fraction of A in the liquid phase, mole fraction of A in the vapor phase. I extend this, so this is x here, corresponding to this x, now I have this y here, which I take to the 45-degree line, I come to this direction, I have another coordinate. Similarly, we can plot different x and y to obtain this, what do we call, xy diagram. So this is also an equilibrium curve, y versus x. The more important here to note is that every coordinate y and x, the temperature is different. It's very important that you understand this, although we don't specify temperature here, but temperature is different for every y and x. Okay, so Txy diagram is one type of equilibrium curve, and more simplified version, if you call it, is y versus x, which is also very widely used here. We were talking about the relative volatility. All right, if A is more volatile than B, okay, you will expect that alpha will be greater than 1, and larger A is volatile than B, alpha will be larger than 1. From here we can show that, or one can see that. Now if you want to plot this liquid vapor equilibrium curve for a larger volatility, then there will be a separations, more separation. In other words, if you plot it here, this will be now wider liquid and vapor curve, bubble point curve and the dew point curves will be wider here. That means for the same temperature, if you go this way, now you look at this difference between y and x will be larger. So that means it's more separation here. This phase is much richer in A than here. And similarly for this, if you want to plot y and x versus diagram by the same technique, by taking the projection here, one can show that this 45-degree line, now y versus x curve will also be, y versus x curve, this curve will also be away from this 45-degree lines. So for the same curve, same plot, if you want to plot for different relative volatility, it's easy to show that. And here what we have done is increasing relative volatility. It's 45-degree line, and away you are from 45-degree lines, you have y much larger than y1 greater than y2 greater than y3 for the same x. So we have plotted yx diagram for different relative volatility. All right. So these are the things which we have to understand both physically and also from mathematically. We can write down all these Rawls-law equations. We can also write down this relative volatility expressions alpha to convince ourselves the shape of Txy diagram, wider it is, that means mode separations. Y is much larger than ZF, ZF is much larger than X. And we have very small relative volatility. These curves, they coincide or they come closer, we have very less separation. Okay. You can write down these equations for Rawls law, and one can do this kind of exercise. As I leave this as an exercise, you must try to convince yourself. Similarly, if you plot Y versus X diagram and draw this 45-degree line, if you have very small relative volatility, this curve will be very close to this Y, this 45-degree line. And you have a larger relative volatility, that means A is more volatile than B, it exerts more vapor pressure than B, then the curve will be away from this XY diagram. This is what we have done here. Now these are all for ideal systems, okay? And we said that we are fixing the pressure here. Now if we change the pressures, Txy diagram will also change, right? So now we are saying that Txy diagram we want to plot for different pressures, P1, P2, P3, etc. Okay. There also qualitatively you should try to understand that if we increase the pressure, then there is a possibility of that means we are trying to approach critical pressure of A or B. Okay, since A is more volatile than B, then at a certain pressure there is a risk of pressure reaching the critical pressure of A. In that case, there is no phase separations, right? If you recall from thermodynamics, once you reach a critical pressure, then you essentially have reach a stage where there is no L and V separations. So if you want to plot Txy diagram for different pressures, one can plot qualitatively like this. So let us plot this pressure effects. Okay, so we have Txy diagram, what we did earlier, X, Y, we have Txy. So let's see if we have, let's say that we have plotted this Txy for certain pressure. So we have Tb, Ta, and this are corresponding to some pressures P here. Now if we increase the pressure, then you will expect that now we have the new Txy diagram, which will be slightly more compact. In other words, now the separation between two phases has gone smaller. If we further increase the pressure, there is a possibility that we might reach the critical pressure of A. In that case, this curve will shrink, it will become like this. So that means now there is no separation corresponding to this zone here. We have liquid plus vapor, we have vapor. Again for the system, here only this is a region where we have liquid and vapor. If we further increase, this curve will further become narrower till we reach a pressure where we have exceeded the critical pressure of B components. So this is like increasing pressure. We have plotted Txy diagram. Corresponding to this Txy diagram, if we just underneath this, if you plot Y versus X, again qualitatively you should be able to judge that if this is the curve for the lower part, right, for a pressure, and then if you increase the pressure, then this will become flatter and flatter. It will approach Y this 45-degree lines till you will have situations like this where there is no liquid and vapor separation. It has hit the 45-degree lines like this and like this. So this is now increasing pressure. Again Txy diagram which we have plotted from this Yx diagram which we have plotted from here, one can take the projections of Y and X, take X here, take Y here, go to the 45-degree lines and connect with this X, etc. So one can do this. The idea is that here we have plotted this Txy diagram or XY diagram or YX diagram for change of the pressures. At higher pressures, in general, most of the ideal solutions, they behave like this. The separation is less, the curve becomes narrower and narrower. Okay. Now these are all for your ideal solutions, right? Now there are some non-ideal solutions where we have very typical things, what do we call azeotropic mixtures, in which case the total pressure is actually more than what is predicted by the Rawls law. So we call it positive deviations from ideality. Similarly, you can have different type of A plus B binary components where the deviation is negative. That means the pressure, total pressure is exerted is smaller than theoretical calculations. Now, when we have this type of situation, isotopic compositions, a very peculiar thing happens, that at certain temperature, in between the boiling temperature of pure component B and A, there is a isotopic compositions, at which entire liquid will be converted into vapor phase without any phase separations. Now, if that happens, you can imagine that in distillation column, at that tray, wherever it happens, the distillation will stop. There is no enrichment. Remember, if we started with A plus B for a liquid phase, we had ZF, we heat it, we reach a dew points, sorry, bubble points, we further heat it, the liquid mixture is now boiling, we have a vapor phase composition Y, which is greater than ZF, and ZF is greater than X. So there is a separation here. We are doing enrichment, we are purifying it. We have vapor which is richer in A and liquid which is richer in B. So this is where we have achieved the separations. Now, if we have this isotopic mixture, or what we call constant boiling mixture, then at that compositions, you will see that entire liquid is converted into the vapor phase. Okay, that means there is no separation there, and one has to avoid this isotopic boiling mixture. For this course, or most of the discussion will be confined to this ideal system, but we must make a note of this non-ideal mixture. So today's lecture we complete with this qualitative description of this non-ideality in binary component mixtures. So we have non-ideality. Okay, say let's take PT is greater than PT ideal. So what we call is positive deviation from Rawls law. Okay. So what Rawls law predicts, now we have pressure greater than this. For that such type of system, as we said earlier, that if we plot Txy diagram, then what we obtain is something like this qualitatively. Now we have Tb and we have Ta, and the bubble point curve, it reaches a minimum before it increases to this Ta, and we plot the dew point, then we have curve like this. So notice here, if we have this composition mixture of ZF as a feed, and if we heat it, then entire liquid will be converted into vapor without any separation. There will be a separations if we take a mixture smaller than ZF. If we increase it, we have the bubble point curve here. Bubble point, first bubble is formed, liquid starts boiling, there is a separation here. This Y is greater than ZF, further heat it, Y is greater than ZF, till we reach this dew point. Okay, so any region, any composition smaller than this ZF, or we call it isotopic composition, you should notice that Y is greater than X. All right, and if you are here and draw a tie line, it's not difficult to show that now we have just the reverse situations. This is also a dew point curve, and this is also a bubble point curve here. Now we have X greater than Y, and if you have a mixture here, that means there is no separation at all. Entire liquid is converted into vapor. This isotopic composition, that's why it's also known as constant boiling temperature. Okay, so only in this region, as long as the vapor, as long as feed composition is smaller than ZF, we have vapor enriched in richer than your feed compositions, and the liquid is leaner in A and richer in B. On the other hand, if the feed composition is greater than isotopic composition, then we just have a reverse conditions. X is greater than Y, A is richer in the liquid phase rather than in this vapor phase. It's a non-ideality situations. It arises because total pressure exerted by such component is greater than what is predicted by this Rawls law. Corresponding to this Txy diagram, if we plot Yx diagram, and if we have this 45-degree line here, and you take the projections from the top to the bottom, you should be able to convince yourself that you will get a curve like this, where now this is the isotopic composition. And notice here Y is greater than X. it's above 45-degree line. So this range y is greater than x, and this range here, this curve is below this 45-degree line, x is greater than y. So this is a non-ideality situation, non-ideal components which you may encounter depending upon type of binary components we have. For example, water with most of the alcohols, right? It's a kind of immiscible fluids, and there is certain azeotropic compositions at a given pressure, at which if you have that compositions, then entire liquid will be converted into vapor, and there will not be any separations. So if you want to separate this type of mixtures, one, of course, the feed composition should be smaller than this azeotropic composition, or if you increase the pressure, there is a possibility of removing this azeotropic compositions. Just now, in the case of ideal mixtures, we plotted the effect of pressure when the curve of the XY diagram changes. Similarly, one can show that if you increase the pressures, there will be a locus of azeotropic mixtures, and this point will move away to one or pure component of A, in which case it's possible to increase our feed compositions at which the distillation or the separation is possible. So as we said earlier that for this course distillations, we confine our discussion, calculations, or the design of a distillation column for an ideal binary component system. We can apply Rawls' law without bringing this activity coefficient, etc., which accounts for non-ideality. Okay.